Now I'd like to talk about some advanced techniques for solving AC circuit problems. So the good news about solving hard AC circuit problems is that because Kirchhoff's voltage law and Kirchhoff's current law still apply, like we talked about earlier, it still has to be true that all of our other techniques that relied on those also still work. So we'll just go through kind of the list of things we've talked about. First is the voltage divider, and we will get back to this later or maybe in the next lecture video. And our voltage divider equation looks pretty much the same, but the voltage across component X, instead of having the ratio of the resistances, it is the impedance of component X over the impedance of all of the things together in series times the applied voltage E, whatever that is. So this is super useful. We will see it again for sure. We also have superposition. If we have an AC circuit with more than one source, we can solve that circuit for those individual sources and then combine our answers at the end. That is also useful. And then the big guns, branch current analysis and mesh analysis and nodal analysis. And remember, these three are really just different recipes or different steps for applying Kirchhoff's laws, in a particular systematic order to give you a system of equations. So when we still apply Kirchhoff's laws, so we're still going to get equations that are correct, and then we just have to solve those equations. So the only downside, the only thing that's harder about doing this with impedances is, of course, all of the numbers are complex numbers, or in general, the numbers can be complex numbers. So solving the system of equations, practically speaking, if you're doing it by hand, it can be harder. If you're doing it with a computer, it might not be any harder. You just have to type in plus and minus i's, and then when you click run, you get complex answers at the end. So it turns out if you are using a computer to solve things, these are basically as easy as doing it with resistors, which is really quite convenient. We'll do an example of this at the end of this video. So these are our solving techniques. In addition, there are some other things that we've learned about that is true for AC circuits as well as DC circuits. The Thevenin equivalence of a circuit is also still a thing. So remember, for resistors, Thevenin's theorem said, any circuit that is a mess of resistors and voltage sources and current sources, so whatever tangled mess we can come up with here, this is exactly equivalent, with respect to whatever is connected at these 2 points. From these 2 points, it feels exactly equivalent to a single voltage source in series with a single resistor, where we just have to find these values R Thevenin and V Thevenin. So this is for our DC circuits. For AC circuits, it's exactly the same, except here we can have any tangled mess of resistors, inductors, capacitors, and AC voltage sources and AC current sources, which are usually drawn like that. But we won't encounter AC current sources. So between any 2 points attached to whatever tangled mess is here, this is exactly equivalent to an AC voltage source in series with some impedance Z. So this doesn't have to be, in general, this will not be a resistor value or inductor value or capacitor value. It will be at an arbitrary angle with some number of ohms magnitude. So this is our Thevenin impedance, and there is still a Thevenin voltage source to find. The technique for finding these values is basically the same as it is for resistors. There are a couple different recipes you can follow, but one is to find V, you can say what is the voltage between the terminals with no load, meaning like an infinite resistance connected to it. In other words, if you just analyze these as like voltage points you're measuring with nothing connected. Okay, and then Z Thevenin is the equivalent impedance you get when you short out all the voltage sources and open circuit all the current sources in your circuit. So what is Z equivalent if all voltages are set to 0? And this is, of course, the equivalent impedance between these 2 points, between points A and B, as we've labeled them here. Okay, so this is also useful in the same ways that our Thevenin equivalence up here is. Certainly, if you're analyzing a circuit for a bunch of different loads, it is much easier to figure out the equivalent and then just treat it as a little 2 impedance voltage divider to see what's going on. And also it means that in general, if you have complex circuits, you can kind of predict how their output is going to change under different loads if you have some model and for like something like a power supply, you would call this Z the output impedance, and that is an important characteristic of different instruments. So yeah, this stuff definitely matters. All right, let's do a little branch current analysis example just to show you how like this really isn't that much more complicated than the resistor stuff. So let's say I have an AC circuit with a voltage source that is 6 volts, and that is connected to the following components. And rather than specify a frequency, I'm just going to give you reactance values for the inductor and capacitor. So this is a 1 kilo ohm resistance. This is a 3 kilo ohm resistance. The capacitor here has a 2 kilo ohm reactance, and the inductor has a, 5 kilo ohm reactance. Okay, so branch current analysis, what do we do? Who remembers? We define 3 different currents because we have these 3 different branches of our circuit. So I'll define one current, I1, going like that, and that, of course, is going through both of these. And I'm guessing that is going to split into current going this way through that branch and this way through that branch. Hopefully that makes sense. But if we guess wrong, we're just going to get a different, we're going to get a current that's different by 180 degrees, right? Which is a minus sign in complex land. Okay, and we'll call that I3. So to start with, let's do our little loop around the left part of the circuit. So starting here, going up around like that, and back to where we started, right? So when we do that, going across our voltage source, so if our voltage source, we're assuming that our voltage source is connected like negative and positive with respect to this 0 degree phase. If we're not told that, we're just going to assume that this will be like what we are measuring things relative to in terms of the phase. So going from here to here, we have 6 volts at 0 degrees. So we are summing all of our delta V's, right? So this is equal to 6 volts. We'll just drop our units. We're just going to leave it as 6 volts. And now we're going in the same direction as I1 through the 1 kilo ohm. So this is minus 1 kilo ohm times I1. And then we're going in the same direction as I2 through the inductor. So that's also minus. And now it is going to be, this is going to look something like minus Z times I, right? Anytime we're going in the same direction as the current, it's minus Zi. Anytime we're going in the opposite direction as the current, it's going to be plus Zi. Just the same, we're treating these the same way we treat resistors in terms of the plus and minus signs. So here, our impedance is 5 kilo ohms at an angle of plus 90 degrees. So that is J times 5 kilo ohms, and the current is I2. And now we are back to where we started, and therefore these three have to equal 0. All right, let's do another loop. Let's do this loop over here on the right. I'm not going to draw the red line, but we all know what this looks like. So starting down here and going up, now I'm going the opposite direction I2. So I have a something that looks like plus Zi, right? So that's going to be plus J times 5 kilo ohms times I2. And now we're going down through the capacitor in the same direction as I3. So that's minus Zi again. And now Zc is minus J times Xc. So this is minus J times 2K times I3. I'm putting these parentheses in there because Z, Z is at an angle of minus 90 degrees, and that's where this minus sign is coming from, the capacitor. This minus sign is coming from which direction we're going in our Kirchhoff voltage law walk around the circuit. So these are going to cancel out. Okay, so doot, and now we have I3 through a 3 kilo ohm resistor, and that equals 0. Okay. And lastly, we have a point at which these three currents meet, and that tells us I1 is equal to I2 plus I3, voltage in equals the two voltages out. And now we have a set of 3 equations and 3 unknowns, linear equations just with complex coefficients on them that we can solve. And we could clean this up a little bit. This minus sign cancels with that minus sign, so we get a plus here. Take away some of our parentheses. So it doesn't look like, we could combine these two terms. So this is like I3 times J times 2K minus 3K. But anyway, so we can put this into some solvers, not other solvers, but like Mathematica deals with complex numbers very easily. You just type it into the same solve statement and it gives you your answer in complex numbers, which is what I did. So I'm going to give you the answer. I also verified this in a simulator. So I ran a simulation of this and got the exact same numbers. So that's a good sign. Mathematica, of course, gives them to you in fraction form. So I had some really big fractions with real and imaginary parts. So that was not maybe the most useful. So I turned them into decimals for you guys. So I1 is equal to 1.146 milliamps. I2 is equal to 0.974 milliamps. And I3 is equal to 1.351 milliamps. And I'll pause here for a second and point out that if I look at this equation, I1 equals I2 plus I3, the way I've written these, that is not true, right? 1.146 does not equal 0.9 plus 1.35, like not even close. And the reason is I've left off my phase angles, right? These are still complex values. These currents are not exactly in phase with our voltage source. They're shifted positive or negative by some amount, and that amount we got when we calculated this. So these were the magnitudes of the complex numbers that were the currents, and then we also have the angles of those complex numbers. So this was minus 9.2 degrees, this was minus 87.9 degrees, and this one was plus 35.8 degrees. So in terms of our voltage oscillation, if we're looking at a graph of if this is our voltage source oscillating, I1 is reaching its peak 9 degrees after. So I1 is reaching its peak like right there. I2 is reaching its peak 90 degrees after. So I2 is peaking like right there. And I3 is actually reaching its peak significantly before the voltage does. So I3 is reaching its peak like that. So, I'm drawing little parts of bigger sine waves. So if you graphed all three of these, you would see some relationship between the currents, something like this. All right, so hopefully this isn't too intimidating. Like I said, it really is the same as the resistors. It's just our values are now, in general, these complex values, but we're following all the same rules.